Hi guys, today we are going to run through some quick notes before I let you go and let you get started on the experiment that we have today. So today we are going to be taking a look at how the different climatic factors end up creating the weather that we have in the world around us, and then we are taking a look at how all of that comes together and can be put into a model that we're studying. So to start us off, just to review, climate is four main things. It's our atmosphere, our oceans, our continent, and our ice formations. So atmosphere is literally the air in the world around us. So that has oxygen gas, it has mostly nitrogen gas, it has some water molecules, and it has some ozone stuff. So when we think about oceans, oceans are really just all of the water in liquid form in the larger masses that we have it on the earth. And that plays a role for multiple reasons, but we'll be thinking about how oceans can have an influence on wind, for example, and definitely on water. Continents are the land formations, whether that be a flat piece of land, a mountain, a hill, a desert, all of that plays a role in climate, and all of those climates play a role in determining what the weather is going to look like. And finally, you have the ice, North Poles, the North Pole. And mostly we're thinking about glaciers when we think of ice. Weather is when all of those climate factors interact and work together, and well, not necessarily work together, but definitely interact together. So weather is when the atmosphere, the oceans, the continents, and the ice all interact. And it's not that they necessarily want to go hang out, right? It's not that the ice wants to go spend time with the oceans or the atmosphere. It's just that they're forced to interact because of the motion of the earth, gravity, and energy from the sun. So energy from the sun provides us with all of the energy that we have, right? It contributes to not cellular respiration, but photosynthesis. It's the reason we have food, and it's also the reason that we have heat on this earth. And with heat comes evaporation, it comes movement of gases, energy in our gases. With the So in addition to energy from the sun, we have the motion of the earth, which is literally the earth spinning on its axis, which plays a role in wind. It plays a role in making sure and sometimes pushing our land forms. So a mountain that's being pushed on its axis, on the earth's axis, it's moving along with the earth. Therefore, it sort of pushes all of the air molecules around it to also move. So just as if I had if this was an air molecule right here and my hand was a mountain moving on Earth's axis, like this is forced to move along with me. Gravity is also a reason that we have interaction between these forces, because gravity is constantly pulling everything down toward Earth. So precipitation happens because gravity is pulling that down toward Earth. We have an atmosphere because gravity is pulling all of those gas molecules down toward Earth. Gravity is the reason that we have oceans that have water in them. The moon's magnetism, if we think about waves, is why we have waves in the ocean, right? But that water still stays in the ocean because of gravity. And also waves sort of push air above it to also move. So all of these things are really related because there's no way to exist on Earth with gravity, but without the motion of the Earth spinning on its axis. There's no way to exist with the motion of the Earth spinning on its axis without any energy from the sun. So all of these forces have to interact, and when they interact, that is weather. So we're going to narrow weather down and pretty much look at it as four different things: temperature, air pressure, wind, and humidity. Temperature is just what is the heat when I walk outside? What do I feel when I walk outside? Air pressure is maybe like we can think of it as density of the air that we feel pushing down on us, and also the air that's moving around in the earth. Air pressure is very closely, directly related to both temperature and wind. Wind moves heat, wind moves water molecules, wind moves air, and humidity is the amount of water vapor in the air. And that will play a role because humidity determines condensation, evaporation, and then precipitation too. So all of those words that I just mentioned are words from the water cycle. The water cycle is something that you learned as a child, but just quickly to review it, precipitation is when water is actually, let's start with water existing in liquid format in our oceans and our lake, and maybe even evaporating from our trees after cellular respiration, our plants, through transpiration. It's breathing out through transpiration. Evaporation is when these solid, or not solid, but liquid forms of water go into the earth. They evaporate and become gas, where they go into the atmosphere and sort of exist as gas. That water that is gas in the air eventually condenses back into droplets of water, and that forms clouds. So clouds, it doesn't have to be like large droplets. In fact, condensation in the sky is definitely tiny, tiny droplets of water. Precipitation is when the droplets of water that form clouds get so heavy because of how much water there is, and it falls to the ground. If you remember, one of the special characteristics of water is adhesion. Water molecules like to stick together because they're happiest when they're sticking together. And so that is why in clouds and in the air, you have water coming together and forming larger droplets, and then gravity pulls it down. So we're going to talk a lot today about evaporation and condensation in particular. So think about those two things as we go. One thing I was thinking about that's interesting is that if you go to a beach and you're like looking at the lake or looking at the ocean on a cloudy day, you're looking at water vapor in the air, or not necessarily even water vapor, but condensed water molecules in the air, and you're looking at a lot of water molecules in the ocean. So pretty much on a cloudy day, the ocean is just looking at a lot of water. A beach is just looking at a lot of water. Anyway, we're also going to review pressure and temperature really quickly. If you guys remember the ideal gas law from chemistry, PV equals nRT. So pressure and temperature are conversely related. As temperature increases, actually they're directly related. As temperature increases, pressure also increases. As temperature decreases, pressure decreases. So I like to think about it in terms of your tires in the winter. If you're driving and it's cold outside, because it's like the first time it's gotten really cold in the winter, your air pressure, your tire pressure light might come on. And that's because it got colder outside. So all of the molecules in your tires sort of started coming closer together. They didn't have the energy to sort of be waving around frantically. They lost energy and they're huddling together. So you might have to take your car to a shop to get more air pressure added to it. Or I guess you could go do it yourself. So, but because you need more air in your tires so that the pressure evens out to be where you need it to be so that your tires function and your car's drives. So at lower temperatures, particles tend to stick closer together and they have less energy, so they're in a more stable state, they're more liquid. When things are a lot hotter, all these particles have a lot of kinetic energy. They're in gas, they're flying around, they're all over the place. So think about that as we talk about pressure and temperature, because when it's cold outside, the air pressure will be maybe lower. And when it's hot outside and all of those molecules are moving around more, the air pressure might be higher. That's not always the rule of thumb because, again, the number of water molecules and condensation and things like that play a role. But that's just a quick reminder for ourselves. When we talk about pressure and temperature, that's what we're thinking about. This image is one that I'm going to have you guys look at on your own, but I'm not going to spend too much time on it because it pretty much reviews everything that we've been talking about. It sort of looks at how the sun pushes energy on the earth, and that energy leads to evaporation, which then, once there's enough vapor in the air, in the sky, and clouds, comes down as precipitation. It looks at how the lithosphere and the surface of the earth sort of determines how wind and precipitation play a role in the greater climate and weather. This is a diagram of what we're about to look at, air. If you guys, again, take a deeper look on your own, but I'm just going to skim through some stuff with you right now. At the very top of it, we have at the very, very external layer of our atmosphere, we have the exosphere, which is so far away from the Earth that we lose things because gravity isn't strong enough to hold it in. So if something gets to the exosphere, it might even leave, and occasionally we have some plasma leave through the exosphere. Well, material in plasma form, not plasma necessarily. Our thermosphere is the hottest sphere, the hottest level of the atmosphere. It's about 800 degrees. It's where most of the sun's energy goes and sticks around. Closer to the Earth, the closest to the surface of the Earth, where we live and breathe, is the troposphere. This is sea level. This is where all of our plains are. This is where our mountains and stuff go up to. Life can't exist outside of the troposphere because there just isn't maybe enough oxygen. Troposphere is where all of the weather takes place. Troposphere is where all of our clouds are. Troposphere is where we will spend most of our life, unless for whatever reason you are like flung into the atmosphere. Our stratosphere is right outside of the troposphere, and it's really, really hot for whatever reason. It's a lot, well, it's not as hot as the thermosphere, but it's hotter than the troposphere, too hot for us to live. About 20% of the heat in the stratosphere is because the clouds in the troposphere are reflecting the sun's radiation. So the troposphere and the clouds in that sense are actually protecting us from some UV radiation because it's bringing it back to the stratosphere. The mesosphere, which falls between the thermosphere and the stratosphere, is actually the coldest layer of the atmosphere, I believe, except from, yeah, I think it's the coldest level. And so it can be like 60 to 130 degrees Fahrenheit there, to negative 130 degrees Fahrenheit. So, and that's primarily because a lot of energy is being released from this level. And so the mesosphere is sort of what gives us energy. The energy from the mesosphere comes down into the stratosphere, and a lot of that energy is reflected by our clouds, but some of it still comes down to the troposphere. Anyway, today the experiment we're conducting is sort of trying to mimic what the troposphere looks like above the ocean when it is very, very hot. Atmosphere dynamics, again, you're going to take a look at this on your own, but it looks at how the Earth's pole and axis and rotation influences wind, and it looks at how pressure from air changes. Like this, for example, shows how what happens when there's hot pressure at the bottom and cold pressure coming in from the top. Collision, this is what we're thinking about today. We are thinking about what happens when two air masses of different temperatures and moistures collide. And we're thinking about what happens as a result. So warm air rises, and then when it cools, it condenses and it condenses and comes down. And that can force lighter air upward and colder and heavier air downward. So a cold front is when you have, let's see if we can zoom in. So a cold front is when cold air is pushed by wind and it collides with warmer air. That warmer air is driven upward, and the water vapor in that warm air condenses and forms clouds. If the cold front is super, super cold and we have this really, really cold temperature underneath this warmer air that has condensed, what the water has condensed, you can get between rain, snow, sleet, depending on what that is. So again, warm air exists, cold air shoots over, and the cold air will be underneath the warm, pushing the warm air upward. The warm air that has water vapor in it will condense, and you'll have rain and precipitation here. And based on how cold it is down here, will determine what we get as a result. But it could be snow, it could be a heavy downpour, it could be ice, it could be whatever it is. So that is a cold front. On the opposite end, we have warm fronts. So warm fronts are when the wind drags in warm air. Ugh. Work. So the warm front is when the warm air shoots in and there's cold air, right? So warm air will always go above it, and this can generally lead to some precipitation, maybe but lighter precipitation than if it's a cold front. So that might be light snow, light rain, or light sleet as a result, and light winds. But if you have cold air coming in, that's when you have stronger winds. So the example that I show you guys of the experiment, the demo I do, has a lot of cold air pretty much coming in and pushing warm air upward. And you guys sort of get to decide how you want to do it. If you're able to maybe bring in a heater, you totally should, and see what happens. But that is it for our notes for today. Oh, actually, one last thing. You guys, again, spend some time and look at this on your own. But it's talking about how auroras exist in the sky, and solar wind pretty much plays a role in making that happen. So take a look at that. But today, for the rest of the day, I want you guys to try out that experiment that is based on cold and warm air meeting and see what happens. Let me know what you think. Goodbye.